Okay, so if you had me for the first quarter, we spent some time talking about the periodic table and how to use it to define a strong acid or a strong base. And one of the things that everybody tells you is, well, you can just memorize this table given in the book. And what I'm about to show you is that you sure can if you want, or you can take a look and realize that the periodic table pretty much gives you all the information that you need to know what's a strong acid and what's a strong base. Now, if you look over here, I have circled chlorine, bromine, and iodine, and sulfur and nitrogen. And so I'm going to start with just the chlorine, bromine, and iodine, and hopefully this sounds a little familiar. You have HI, HBr, and HCl. And those are all of our strong bases. Let's do that a little neater. I'm sorry, strong acids. HI, HCl, HBr. Cool. So why not HF? Hopefully that's a question that you've asked yourself at some point in time. And there's several reasons for that, really. One of the kind of easiest ways to remember that is that if you go across the periodic table, there's something that's happening to our atomic size. We are coming down here and our size is decreasing, right? Because we're adding more and more electrons as we go left. And as we add more and more electrons, we're actually decreasing the size of that atom. Cool. So fluorine is so similar in size to hydrogen, and it has the same sort of orbital configuration, or orbital, I can't draw it here. But if we were to draw little circles here, we'll do it here. Horrible circle. Let's make a small circle for hydrogen. And fluorine is only going to be a little bit bigger. And these two make a nice overlap as far as their orbitals go. So the similarity in size leads to a very strong bond between the hydrogen and fluorine. Well, that and our electronegativities. Okay, so we have similar size, strong bond, therefore it doesn't easily dissociate in water. And remember, our definition of a strong acid is something that easily dissociates in water. So fluorine is not on our list of a strong acid. Our hydrogen, our HI, our HCl, and HBr are. These are all strong acids. They will completely dissociate. So why did I circle sulfur and nitrogen? You've never done anything with HN or HS. That doesn't sound familiar at all, I hope. And the reason why I circled it is because, well, you haven't seen anything regarding, or just specifically just hydrogen and nitrogen. You certainly have seen HNO3, and you certainly have seen H2SO4. Okay, so these guys, when we're paired with oxygen, form strong acids. And we have the same kind of trend going on here as far as the interaction between the nitrogen and the hydrogen, or I'm sorry, the nitrogen and oxygen and the hydrogen, and the sulfur and the oxygen. And then the last one to remember then is just HClO4. So again, you can memorize this, or you can just look at the periodic table, and we can look as far as going closer to the oxygen. We're going to get more in depth here in, before the end of this chapter on what exactly these pictures look like, more than just me drawing squiggly lines on the page. Okay, so those are our strong acids. Now what about our strong bases? So this should look familiar, these guys here. And then some guys here. Because remember, there's 6 of them. So we go all the way down. I think your book stops at, yeah, barium. So what's not true is that these guys down here aren't strong acids. And I have a video that I showed in Chem 121 that shows how strong those reactions are with water. And so while they are still strong strong bases, while they are still strong bases, they are so reactive, they're just not anything that we work with. So now we start here at calcium, and you should notice that this is in line where we have our d orbitals over here. So we're getting bigger in size. So remember, this line here is all our OH2 because this is a +2 charge, right? So Ca is going to have, our hydroxides have a -1, so there it takes 2 of those. So the atom has to be big enough for these 2 hydroxides to get in there. Magnesium is not big enough. It is, oops, sorry about that. Go away. It doesn't have the extra shells to build on, and it doesn't have anything giving it enough space to add in those hydroxides. In fact, if you add water on top of magnesium, you will get some hydroxide, some magnesium hydroxide out of that, but you're just not going to get a bunch. It's not going to do a whole heck of a lot. But again, when we start putting the calcium, the strontium, and the barium in water, you start seeing some pretty interesting and very rigorous reactions. So it's pretty cool. Don't throw them in water, though. You don't want to raise the pH in a puddle. So then we have BaOH2. And then the standards are lithium hydroxide, sodium hydroxide, and our potassium hydroxide. Now, I always give you a periodic table. So if you can look at the periodic table and remember this little piece of advice or information, then you can pull out the strong acids and bases all on your own without having to worry about memorizing any tables. All right, so now let's go back to here. So what happens if we have a weak acid? I think your book gives you, what does it give you? Acetic acid. So we have HC2H3O2 plus H2O. And I have this little thing that I wrote up top for equilibrium. I just wanted to talk about that briefly. We're going to get into more detail as we move on. H3O plus C2 H3 O2 minus. Okay. So these guys here, this kind of interesting looking arrows, those represent equilibrium. So that's just saying, oops, I want darker ink. That's just saying that the reaction is going both ways. So this is a weak acid. It doesn't completely dissociate. So it's not like we can say we're going to put it in with, okay, I did that right. We're going to put it in with water, and so long as we have the proper proportions, we're going to have a complete reaction. In this case, when we have something that's weak, we can't have a complete reaction because it doesn't completely dissociate. So think about it as going square dancing. I know you probably have never done that, but they change partners a lot. You know, everybody's running around the dance floor and swapping partners on the dance floor. And the same thing's going on with these ions. So that's where this equilibrium exists, because as a partner is swapped here, then that means that I've picked up a hydrogen and that somebody else is going to be liberated. And so it just continuously goes back and forth. And we're going to talk about how to determine the degree of equilibrium and how much of a product is going to be predicted to be produced later. But for now, I just want you to understand that those arrows mean that something is in equilibrium. So we have a kind of constant back and forth that's going on with our products and our reactants. So those are the biggest and the last pieces of the Arrhenius acids and bases, and now we'll move on to Bronsted-Lowry.